Math 2415, Calculus 3, Multivariable Calculus, Chapter 10, Vectors in the Geometry of Space, Section 1, Three-Dimensional Coordinate Systems, Video 6, Inequalities in 3 Dimensions. This will be the final video for Chapter 10, Section 1. Now, I'll go ahead and tell you right now that the stuff you're about to see in this video, I don't think is that difficult, but then again, I'm a little bit biased. However, when we get to Chapter 12, the middle of Chapter 12 and start doing triple integrals, or even double integrals in 3 dimensions. The regions that we're going to be integrating over are not just going to be intervals on a number line. Like when you do an integral in Calculus 1 and Calculus 2, we had some function, y equals f of x. This goes all the way back to the beginning of integrals. And when we found the integral from a to b of f of x dx, at the very outset, it told us the area underneath that curve, or the sum of the areas of the regions between, well, you know what I mean. Let's just assume the curve is above the x-axis. But when we stretch this to 3 dimensions, we're going to have some other obstacles to overcome. For example, when we do this integral here in 2 dimensions, it's a 1-dimensional function in a 2-dimensional space. Then we integrate from a to b, so we integrate over that 1-dimensional object. But when we bump it up a dimension, we're going to be integrating over a 2-dimensional object. And there will be situations where we might integrate over a 3-dimensional object. So we're going to have to describe these objects in terms of equations and inequalities. For example, the inequality here would be real simple. The inequality here would be a is less than or equal to x is less than or equal to b. That gives us that segment on the x-axis. But when we bump everything up a dimension, the thing that we integrate over goes from a 1-dimensional object to a 2-dimensional object, and a 2-dimensional object could be a rectangle, it could be a semicircle, it could be a triangle, it could be any closed simple region, if you will. And so we're going to have to get really proficient at describing regions in 2 dimensions and surfaces in 3 dimensions. And a lot of those are defined by inequalities. So for example, let's sketch and describe the solid defined by the following inequalities. X is between 0 and 2, which is a more intuitive way of saying 0 is less than or equal to x is less than or equal to 2. I'm bigger than 0, but I'm less than 2. So I'm between 0 and 2, and I can be 0 or 2. So x is between 0 and 2, y is between 0 and 2, z is between 0 and 3. Well, this actually isn't that hard to do. I know I say that a lot. I'm not going to be as froofy with my x, y, and z axes, because it's a lot faster to draw that than to set up all the other pieces. So what does it mean for x to be between 0 and 2? Well, that means x can only go between here and here. So let's draw a little segment here. So my x has to stay between there and there. What does it mean for y to be between 0 and 2? Well, the exact same thing except in the y direction. So my y can only be between 0 and here. And what does it mean for z to be between 0 and 3? Well, same thing except in the z direction. Z has to be between 0 and 3. So as I navigate around space, I can only keep my x's this far, my y's this far, and my z's this far. So can you picture what shape I would get, what 3-dimensional object I would get if I were to allow the x to fluctuate over its entire interval, and y to fluctuate over its entire interval, and z to fluctuate over its entire interval? Well, let's think about it. This segment is what my x is allowed to do, but it's allowed to move left and right by 2 because of the y, and up and down by 3 because of the z. And similarly, my y can fluctuate its x's between 0 and 2, and its z's between 0 and 3. And similarly, this segment can fluctuate its x's between 0 and 2, and its y's between 0 and 2. So can you see the object that it would draw if I let all those things translate in the directions and the distances they're allowed to go? And the answer is it would draw this rectangular prism. Doing my best to draw it in 3 dimensions. Here comes the fun part. I draw this box. Okay. So that's what it would look like, and I could define it as there's a lot of ways to describe it. It's a rectangular prism of dimensions 2 by 2 by 3. 2 in this direction, 2 direction, 3 in that direction, so its volume is 12. It's in the first octant, and one of its vertices is at the origin. Where's the other vertex? In other words, where's this? Well, to get there, I would have to go 2 in the x direction, 2 in the y direction, and 3 in the z direction. In fact, I could come up with the coordinates of all of these if I had to. What's this one? Well, its x is 0, but its y and its z are 2 and 3. And I could do the same thing with all of them. So it's a box. Cool, piece of cake. What about this one? It's missing a piece. 1 second. All right, there we go. It was missing its squares. Sketch and describe the solid defined by the following inequalities. Inequality number 1. X squared plus y squared plus z squared is between 4 and 9. Inequality number 2. Z is less than or equal to 0. Okay, let's focus on the first one. Actually, let's talk about the second one for a moment. What would it mean visually in the 3-dimensional coordinate system for z to be negative? Where is that? Where are the z's negative? Well, down here, but not just on the z-axis, anywhere below the xy plane. So in other words, down here is where the z's are negative, but that highlighted inequality makes no stipulations on x's and y's, which means I can move this in the x direction any way that I want, and I can move it in the y direction any way that I want. So where are all the points where the z is negative? And the answer is all the points on or below the xy plane. I say negative, I should say non-positive. So it's the bottom half of space. Half space is actually a correct way to describe it. So the yellow part means we only want the parts on or below the xy plane. Okay. But what does this inequality mean? Well, we can look at it from one of 2 perspectives because I recognize the expression in the middle. That was supposed to be red. Hold on. I'm not sure what just happened there. I recognize this from a couple of places. Number 1, it looks like the left half of the equation of a sphere that's centered at 0. Number 2, I could almost think of it as a distance from the origin. And I wish I had mentioned this in the distance formula video, so I'm going to bring it up now. But the distance between the origin and a generic point x, y, z, the distance is equal to the square root of the sum of the squares of the differences of the coordinates. But because one of the points is the origin, x minus 0 is x, y minus 0 is y, and z minus 0 is z. So when I see x squared plus y squared plus z squared, I can also think of it as when under a square root, the distance from the origin. I'm going to take the spherical approach because there wasn't a square root in this inequality. But if you read the book, because I borrowed this example from the book, I might have modified a little bit. What it actually says to do is to take this inequality and square root all 3 parts of it, which is a viable thing to do because as a function, square root is increasing. And this is getting a little bit of theoretical stuff. Pardon me. Excuse me. This is getting into some of the more theoretical stuff that some calculus students don't experience. But when you have an increasing function like f of x equals the square root of x, then it preserves the order of an inequality when you apply it. For example, if I square root all 3 of these things, then the inequality is going to be preserved because bigger things come out bigger and smaller things come out smaller when you square root them. If you have a decreasing function, it would actually reverse the inequality, but let's not get too nitpicky. Let's just focus on this as spheres. So what does, and let's even trim this down a little bit more. Let's just look at, I'm not sure what happened there. Let's just look at this part of the inequality. What would it mean for x squared plus y squared plus z squared to be greater than or equal to 4? Well, let's start by thinking what it means for x squared plus y squared plus z squared. That's a horrible z. What would it mean if it equaled 4? Well, that's easy. It's a sphere whose center is 0 and whose radius, center is the origin and whose radius is 2. So I could draw a sphere of radius 2 pretty easily. What I would probably do is just go up and down 2 and left and right 2. In other words, focus on the x and the y axis. The y and the z axis. And then just kind of give it a little bit of depth in the x direction. So there's a sphere of radius 2. But that's what it means for x squared plus y squared plus z squared to equal 4. What would it mean if I said, no, I need that to be greater than or equal to 4? Well, equal to 4 means on the sphere. Where are the points where x squared plus y squared plus z squared is greater than 4? Well, think about it for a second. If this number were greater than 4, then its square root would be greater than 2. So from a spherical perspective, it would be more than 2 away from the center. So what this part represents is the exterior. This represents the exterior of a sphere centered at the origin with a radius of 2. Because it's greater than or equal to, I have to exceed the radius, or rather the square of the radius in this inequality. So I have to exceed the radius on the sphere. So I have to go, I could be on that sphere on the or beyond. But what would it mean on the other half of this inequality, where x squared plus y squared plus z squared is less than or equal to 9? Well, I know what it would be. Let's put that back in black. I know what it would be if it said equal 9. This would be a sphere centered at the origin with the radius of 3. So I would have to go one more out on all my axes. And let's do this one in blue. And then here's the x, the yz part of it, and then I could draw the x part of it here. So we got a larger sphere encompassing the smaller sphere. But that's what it would say if it equals to 9. But it wasn't equal to 9. It was less than or equal to 9. So what do you think those points are? Well, if I have a number less than 9, then its square root is less than 3, meaning that this includes the points whose distance from the origin is less than 3, which relative to the blue sphere would be inside the blue sphere. So if you put it all together, the first compound inequality basically says all the points on or outside the red sphere, but simultaneously on or inside the blue sphere. So it's almost like a hollow ball. You ever had a tennis ball and cut it open and notice that it's got a certain thickness? So you can think of it as one sphere with a sphere removed from the middle. That's what this would be. The yellow inequality represents all the points between these two spheres and possibly on the surface of either one of the spheres. But that's not what this particular problem's picture would look like, because remember, we also had the inequality that z is less than or equal to 0. And we already decided that what that meant was on or below the xy plane. So if we put it all together, I got to be on or below the xy plane, outside the red sphere, inside the blue sphere. So how would that look? Well, let's see if I can doctor this up a little bit. Get rid of the circles for a second. Actually, I won't bring that back. I'm going to do something else. I'm going to color over it, but I'm going to color over it in white. See if this will work. That's not working. Let's try it this way. There we go. So let's get rid of the top halves of these. So goodbye to you. Unfortunately, I can't just erase the top part of the circle because it would get rid of the whole circle. And let's get rid of the top part of that, because we're only looking on or below the XY plane. And now let's put a little bit more clarity on this picture. Let's see. On the XY plane, it's too thick. Let's take that down a couple of notches. On the XY plane, the top of this hemisphere would go about right there. Actually, go out to 3, which is out here. And then for the red sphere on the XY plane, it would go out to 2. So my negative x-axis got a little bit janky. But it would be, well, it would look like half of an avocado if an avocado were round and you remove the pit. So let me see if I can fill this in a little bit. Let's use I don't know if I'm gonna use black. Let's use brown. That's not filling it in. Here we go. All right, so it looks like it would be basically the bottom half of a tennis ball if you cut it in half. Or maybe a cantaloupe. Yeah, that's good. Like half a cantaloupe. That's good. All right. Dang, now I'm hungry. Well, it's dinner time and it's 6:28 p.m. on a Monday night. So there are other inequalities, but just keep in mind that if you have a greater than or less than usually means a distance less than what you're saying, and greater than means greater than, obviously. So when it comes to spheres, less than means on the interior of a sphere, greater than means on the exterior of a sphere. We could even find the volume of this thing. It wouldn't be that hard to do. We could find the volume. In fact, I'm gonna, just because I brought it up. If you don't want to find the volume, stop watching the video. But the volume is going to be, let's think about this. The blue sphere had a radius of 3. So its volume is 4/3 pi 3 cubed. And then we remove the inner sphere, which had a radius of 2. So 4/3 pi 2 cubed. But then we took the bottom half of it because we were on or below the XY plane. So it's only going to be half of that. Let's factor out a 4/3 pi and have 1/2 times 4/3 pi. 3 cubed is 27. 2 cubed is 8. 2 goes into 4 twice. 27 minus 8 is 19. So this becomes 19. And then in the top, we have 19 times 2, which is 38. We still have a 3 in the denominator and a pi. So the volume of that half tennis ball is 38 over 38 thirds pi, or 38 pi over 3.